Is that? So I've added some more problems to this list. It's funny if you start typing Kyoto problems, the spell checker suggests Kyoto protocol. Okay, maybe we'll start with a discussion. What's a quantum group? Maybe first start with a finite group. Finite group. So to a finite group, we can associate its group algebra. Let's say we're complex numbers. So this would be by the Peter-Weil theorem. This is direct sum over A reps V of all endomorphisms. And so in some sense they have this group and this algebra have the same representation theory, but there's some information lost, right? So you can't really, only thing you remember is just dimensions of reducible. Like for example, all abelian groups with the same order. Say if I have an abelian group, you'll just get direct sum of fields. All this map remembers is just the order of the group. And so how do you remember the group in this map? And so the answer to this is the following: that this is not just associative algebra. If we have a group, we have a tensor product of representations. So the group has a group representations. So if we look at the representation of a group, these representations have tensor product. So if I have maybe. So actually in my notes, I think I denote, there's so many V's in the subject. Maybe I will change this to M module. So so an element G acts in a tensor product of two modules by acting as G in the first factor and G in the second factor. This means from this algebra there's a homomorphism to its tensor square. Which sends G to G tensor G. So if I have a tensor, so if an algebra tensor product of two modules, naturally module over tensor square. And so if I have a map from an algebra to its tensor square, I know how to act on tensor product of modules. So this means the group algebra of a group has an extra structure which the general algebra doesn't possess. You have a map from the group, from an algebra to a standard group. So this map is compatible with so the fact that this is a group. So it's algebra homomorphism means a certain axiom, and the algebra satisfying such are called this extra structure. The structure of it's called bialgebra. This map satisfies axioms dual to multiplication. If I have for example, if I have a multiplication in the group, multiplication in associative algebra is associative, and this is called co-multiplication. Co-multiplication is co-associative. Means if I want to map to tensor product of 3 factors, I can use it in any order. So this is a very important structure, and the group itself. So the group G may be found inside CG as the set of non-trivial solutions. So maybe we call this map, it's a co-multiplication, usually denoted with delta. So if you solve equation delta of A equals A tensor A, and there's a zero solution, but the only non-trivial solutions are just group elements. So this is a solution of such equation in the bialgebra called group-like elements. So just to say the group itself is just a set of group-like elements in its group algebra. Well, this is trivial, right? Because if I have an element A is a summation of some coefficient Ci, Gi, then delta of A is summation Ci, Gi, then Gi, and this has to be equal. Where is this equal to the product, which is summation over I and j, Ci, Cj, Gi, Gj. This means that there's a zero solution, and the only other solutions are delta functions. So to somehow stress that this structure of coproduct has all the axioms there are opposite to the axioms of multiplication. There's a notion of there's a unit. We have unit, which is just the identity element inside G. The dual notion is the notion of co-unit. This is the trivial representation, which is the trivial representation. This is identity for the tensor product. Right? If I take among all the representations, there's the distinguished one, trivial representation, such as with tensor with a trivial representation, we get our original representation back. And the axioms for this are, you take the axioms of unit and you read them the other way around. It means if you take all arrows and you reverse them, you get from the axioms from unit, you use the axioms of the coordinate. And so what is this? This means the co-unit what I denote in my notes maybe I denote it. Well, maybe not. Maybe I'll call it eta. And so co-unit of summation ci gi. Well, what's the action of this in the trivial representation is just summation ci. So sometimes it's denoted, sometimes people write it that this is like the integral over the group. The identity is the delta function, the identity, and the dual operation is the integral over the group. Well, so far this applies. Doesn't have to be a group for this discussion to apply. Can be any semigroup. There's no. I mean, if it's a semigroup, it's just as well. We haven't inverted anything anywhere. So then, the fact that it's a group, it means we have an inverse of multiplication. So this is. Inverse in group corresponds gives the map S. So this would be S sending summation ci gi. This would be summation, it's a linear map gi inverse, and this has the property this is anti-automorphism. This is clear, so it means S of AB equals S of B, S of A. And the fact that this is inverse from multiplication, what does it mean? It means if I take so the identity that the basic identity. This is G times G inverse equals G inverse times G equals 1. What does this identity mean? This means if I take any element A, and I apply A, if I apply coproduct to that, so maybe S A is summation ci gi. If I apply coproduct, then I get summation ci gi times gi. Then if I take, now I can take antipode in either of the factors. It doesn't matter in which one. Maybe I'll take one tensor antipode, so I'm going to get summation for ci gi tensor gi inverse. And now I use multiplication. So there's multiplication map from the tensor square of the algebra to the algebra itself. And so this is 1. And so I'm going to get ci times the identity in the group. And so this axiom means that the fact that antipode is inverse to multiplication in this sense, this says that if I take the multiplication of one tensor antipode, or antipode tensor 1, then tensor this. So what is this expression? This is first a linear function of my element A. So this is my integral of A. This is the co-unit. This is the co-unit composed with unit. And this is great that this axiom is actually reads symmetric. So multiplication, if you read it like the way so you can this is coproduct is a map from an algebra to its tensor square. So it's usually maybe denoted some tensor like this takes one element and makes it 2. Then you apply antipode in either of the factors. So this is my, then you apply multiplication. And so then you get a map. And so that map is a composition of a canonical map from your algebra to the ground ring, and from the ground ring to the algebra. So this is a get a map from. So this is my, I started with some of my algebra, maybe call it A. Go to A. And so then there is a map from A to ground ring, or ground field. This axiom self-dual, if you read it backwards, you get the same thing. Means that the, and in fact, all set of axioms for here, for if you somehow read the, it's exactly self-dual. I'm not going to write them all. You can find it in Wikipedia. So somehow this is the so axioms. For this product, coproduct axiom unit, co-unit. This gives you the notion called Hopf algebra. And why was Hopf interested in this? Well, it's because Hopf used this to describe the homology ring of a Lie group, say a compact Lie group, because this has a product. Use the usually the cup product in homology, and coproduct coming from coproduct coming from the multiplication map in the group. So this is associative map. The dual map on the cohomology would be associative coproduct on the algebra. And then Hopf's theorem says that then this has to be exterior algebra on finitely many generators. This is a very weak structure. And so in general, this is somehow typical examples of Hopf algebra have something to do with groups. Like, for example, functions on a group would fall, functions on an algebraic group. Say if I take regular functions on an algebraic group, then this has a commutative product and has a non-commutative coproduct. This is in homology. This is so if you look at this, if this multiplication is non-commutative, then the dual operator, the coproduct, would be clearly non-commutative on functions. So it's, let's say, non-commutative means non-co-commutative. Right? So commutative means M is equal to the same if you permute the factors. Permute the factors, multiply, get the same thing. And then there's notion of co-commutative, which is when the coproduct is the same as you permute the factors. So in general, neither has to be for the group algebra of a finite group. The product, of course, is something, and then coproduct is co-commutative. But for regular function on an algebraic group, the product is commutative and the dual operation is not. In general, neither. And so functions on an algebraic group is an example of Hopf algebra. Infinitesimal analog of a group algebra. So if G is now a Lie group, or an algebraic group. Then, like I said, the regular functions on the group. This is commutative, non-co-commutative. Hopf algebra. Hopf algebra. The dual notion, which is more like, so this is the group algebra. So here I don't write the brackets. This is more like, this is like a dual to that. So there's you can take distribution on a group. That will be an example, or more infinitesimal version of that if you take the universal developing of Lie algebra. So these are distributions supported at the origin. This is the opposite. This is non-co-commutative Hopf algebra. Or if I have a set, so if I have psi here, I define its coproduct by the infinitesimal version of this relation. If I take this relation and I differentiate it at g equals 1, so I'm going to get by Leibniz rule, I'm going to get this. And then the antipode is the derivative of inverse is minus. And the action of any psi in a trivial representation is 0. So that's a. And so usually when people say about, yeah.
G, you write commit, non-commit?
This is commutative but non-co-commutative. Non-co-commutative. Yeah, I missed it. So usually these two examples, their deformation in the class of Hopf algebras are usually called quantum groups. So this is what usually called quantum groups. So if you deform, and we especially will be interested in deforming this. So what we want is, and so when we want to relate, so a quantum group of this type, what we want is to relate to spin chain. And so specifically, in our example specifically, we want to look at some particular, we will want to look at some particular quantum group name, what's called the Yangian. So it's the Yangian of GL2. This is a Hopf algebra deformation of the universal developing of, you take GL2 and you consider polynomials with values in GL2. It doesn't have to be complex numbers here, but so this means polynomials. These are polynomials with value in GL2 with commutator coefficient wise or point wise. That's all we have. So, and we will be the there's a traditional way to present this algebra, namely by generators and relations, and which is something I'd rather avoid doing, and because you can means it is very useful to to think about algebras by generators and relations, but it's sometimes even more useful to think about algebras in terms of the category of its representation. It's like if you take an algebraic variety, of course you can define it by coordinates and equations, and this is certainly there's nothing wrong with you define algebraic variety by coordinates and equations. But it's from trying to understand kind of deeper property of algebraic variety, it's much better to think about, what's the category of coherent sheaf looks on this variety. Similarly, algebra is just like object of the same kind. So you can define it by generators and relations, but it's better. I think certainly for certain purposes, it's better to think about the category of its modules, or some category of its modules. And so right. So this is the. I forgot to say before if you have a bialgebra, then its main the main way in which bialgebra structure manifests in category of modules is having a tensor product. And if I have an antipode, then the main way it manifests is that the category of module has duals. If I want my algebra to act in the dual vector space, I need an anti-involution. I need an anti-automorphism of my algebra. So, right. So this is maybe I forgot to say. So this is two things. So S makes S results in duals. So it's two remarks. So first, S introduce the notion of duals in the category of wave modules. In general, they're duals, they're left duals and right duals. So, but let's not worry about it because S is unique when it exists. So it's the same thing in a group multiple in a finite group. If I gave you a semigroup, if it is a group, you'll know it. It's not like there's a if there is an inverse, then it's just set theoretic inverse will be also the somehow. If I have a Lie group, which is some kind, if I have like an algebraic monoid, which is a group, and the set theoretic inverse will be also algebraic inverse. And so this is we won't worry about so much. So this is, but we will be interested in but the tensor structure in the module. Let's be a fair amount. And so okay, so now back to this example. The main or example like that. So more generally, you can take the Yangian of some Lie algebra. This is a quantum group. This is something. So if you have a Lie algebra tensor polynomials in one variables, and you consider a Hopf algebra deformation of such structure, then you'd call this a Yangian. Right. And so very important thing is that this has an automorphism. Namely, these are functions on the line. The line itself has automorphism. And that automorphism will persist to this quantum group. And so if I have two modules, for any module, so maybe I'll call it, or maybe plus a, plus some constant a. So there's a corresponding automorphism. And so for any module, M in any y module M, I have a module M of A, which is obtained by so automorphism of an algebra. I can precompose with this automorphism, and I get a new module. So this is like this is what's a typical module over this Lie algebra. Well, first you just send t to some constant, some value. So then you send t to the some number in my ground field, and then I get I go to u of GL2 C, and then I can take any module here, so maybe call it some kind of module, and then this would be, so to speak, a module sitting on let's C. So if I act by this automorphism, this moves around the position where I evaluate this. So these are called evaluation modules. They're some of the most important ones. So for any module, this is also a module. So the main feature is that this algebra will be not co-commutative, right? Meaning that if I take M1, let's speak A1, tensors M2, A2. And of course, there's a permutation of factors, which is, is different from M2 A2 tensor M1 A1. Like for example, if I permute for this Lie algebra, if I just permute the factors, this is an intertwining operator. And this is will not be the case. It's really different module. But the second thing is that, well, you can ask, well, how can it be really different? because after all, what's before the deformation? What's going to be? What's it going to be? We have some modules. So think about this is certainly. If you evaluate at two different points, you have polynomials evaluated at two different points, of course you're going to get any algebra in the first factor, anything in the first point, and anything in the second point, right? So if I have a module, like for example, if it's a reducible module, I can certainly get every operator. Certainly this tensor probably be irreducible if A1 and A2 are distinct. And how bits it's a different irreducible module with the same gain. It has like the same character and everything. How can it be so different? So it can't really be different. And so the manifestation of that is really there exists for generic A1 and A2. Really A1 since there's automorphisms that shape the one, so enough to require the difference in generic, there exists trivial intertwiner is usually denoted R check of, it's a function of A1 minus A2 because the simultaneous translation is an automorphism. Which is an intertwiner. This is not a permutation, and to highlight that this is not a permutation, usually you single out the permutation and write R. That's what's called R matrix. This is not one, this R matrix. In other words, this matrix that, so there are two ways to define this. You can either multiply in the opposite order, or you can use the opposite coproduct to make the algebra act on the same order. So the R matrix is an operator you take same order but the opposite coproduct. And so this is not one, but this is a morphism for generic A1 minus A2. And in fact, what will happen in this for this sort of modules, for the formation of this kind of modules, this is in fact will be a rational function of A maybe A1 minus A2, which is identity such that R of infinity is 1. This is a normalization condition, not so important. But the fact that this is a rational function means I have a map. It has, I have a map, some rational function. So it means the kernel and co-kernel of that map jump. Right. So this is some kernel and co-kernel of this map, some sheaf on the line of this A line, and this has some scale. And those are the values. So generically there's nothing, but at certain values, the modules really are not isomorphic. In the typical scenarios where modules are isomorphic, and then for a certain value of parameter, you get one is extension of two modules one way, and the other is extension of the module the other way. And so then you get the kernel and co-kernel of the. So then the quotient of the first module goes to the sub of the second. That's your intertwiner map. That kernel and co-kernel set. And so, in representation theory of quantum groups that are so in representation theory, so there's you can ask, why did I start with these polynomials? I could have started with just the universal development of just the algebra itself. It's also seems like a simpler thing. And so if this have a finite dimensional Lie algebra, then there's a similar notion, but there's no place for this zeros and poles of this R matrix. And so this operation having a non-trivial intertwiner between products in different order is called the braiding. Very, very important thing. Here you have a braiding, but the braiding is a rational function of some variable. Slightly more complicated, but very closely related notion. So maybe I'll still call it braiding. And so that means the category of modules of the kind of algebras that I want to look at. This is a category that has tensor products. It's a tensor category. It has duals, and it has this braiding. And then there is so for example And then there's general general reconstruction theorem that says that any abelian category with such data is in fact a category of module over some Hopf algebra. So this is similar to the fact that if I have a tensor category which is a trivial braiding, means the tensor product. So what is the so how do I find, so if I have a a special case of that, suppose I had a trivial braiding, means every product in one tensor order will be isomorphic to the product in the other. So if that is the case, then in fact this is such category will be modules over some, in fact, algebraic group. But so this is the way to read it. There's like for example, there's a recent book by Okounkov and many other people, if I can't remember them all, called Tensor Categories. It's a very good book. I recommend reading it. And so there's the point is there's some general theorem to the fact that you can if you have a category with certain properties, then it has to be modules over certain Hopf algebra. However, there's also a completely pedestrian way to so maybe I'll explain it now. So there's somehow there's there exists general reconstruction theorem. Oh, I forgot to say, sorry. So this, I forgot to say, very important thing, very important notion. If you have, no, it has to be the case. You have to assume that your category has what's called a fiber functor, means has a functor two vector spaces. That, like for representation, that is, that means you just go to the underlying vector space. It's called a fiber functor because originally people were thinking about representation of fundamental group, and so then the fiber functor is just you take a fiber of your flat connection at some point. So this is, there's some tensor categories about which it's unknown whether they have a fiber functor. So it's so there's we will be interested in things that are they're vector spaces to begin with, or maybe free modules over some ring. So then this would be the fiber functor would be given to us. So in fact, but we're not going to use general theorem. There's a pedestrian reconstruction theorem. Pedestrian reconstruction theorem is the following. So you start with so the ingredient of this pedestrian reconstruction theorem is a bunch of vector spaces. Or like I said, you can consider modules some ring, or vector space over fields good enough for us now. You start with a collection of vector spaces. So start. And so you set a vector space as Mi, and operators are Mij of ai minus of some variable a, and this operator is a rational function. Okay. C is 1. This is again, maybe, so they acting in 1 and satisfying Baxter equation. This comes from the fact that if I have a tensor product, what's the Young-Baxter equation? The Young-Baxter equation says if I have a tensor product of 3 modules, I can put them in the opposite order in 3 ways. Sorry, in 2 ways. So, and then the equality of these 2 is so in this context. So if you have a module sum group, you not necessarily. I mean, you could. If you have 2, well, anyway, it doesn't matter. So we require that if I have the 3 modules, so 1 and 2 and 3, and I can put them in the opposite ways, in the opposite direction in 2 different ways. So I can first commute the first 2, then this 2. And this 2. This overcrossing, undercrossing is not important here because they've or I can do the opposite. First I cross this 2. I cross this 2. And I cross. So this means for this matrix R check, I have a relation which is just the Coxeter relation or the braid relation, and for the matrix R, the relation becomes R. So I'll drop. I'll write R1, 2. This will denote R and 1, R and 2. So the relation says that the R1, 2 of A1 minus A2 times R1, 3 of A1 minus A3 times R2, 3 of A2 minus A3. This is equal the other way around. The indices are the same. So this is the input of this reconstruction theorem, and the output would be would like the Hopf algebra Y and the category of modules over Y such that R is the braid. So the construction is first. So how we construct first? The first step, and then the category of module. First, we extend R matrices to tensor product of Mi. So this is done as follows. So if I want to by some module M1, M2, and I want to braid it with M3, M4, M5, then all I do take, so I have some, so I apologize. Right, I have individual, so what I do is I just take a product over all crossings in this diagram. So in other words, my R matrix would be, so I look at the R matrix, M1, M1, tensor M2, and then I braid it with the M3, M4, M5. And this would be, so first I take the R matrix to 3, then I can take then, so this is, just read it, I just read it from top to bottom. First crossing is this one, then I can take either of this, so it doesn't matter. So then I take one, say 1, 3, and 2, 4, and so forth. It means if you have to bring this representation by this representation, well, you can do it by bringing M2 past this one. Just really, this diagram just tells you how to bring the factors in this past the factors there. And so this is this newly defined. I mean, it's clear that it's elementary to see that this is defined. This also satisfies. $5 second. So I will define Y will be sitting in just the direct product. I'll define Y as an algebra of operators in all possible, so direct product of all possible collections of endomorphisms of all possible finite length. So I'd like this to be modules over my algebra, and okay, I'll define my algebra as something that acts in all these modules. And how it is defined? So this will be taken by matrix element of R matrices. So concretely, so if I have some, maybe I have some module M, and I take some other module, maybe called of the same kind. Maybe I'll take it, call it auxiliary representation. So if I take my representation, I take R, take some auxiliary space. Maybe I'll call it I don't know, M0. This auxiliary space and my space. So I have a matrix. And I take the matrix element of this R matrix in the space here. So it means I apply it to some vector. So this is, I apply it to some fixed vector. Maybe better say. So what does it mean? What does it mean takes a matrix element? I take like a trace or auxiliary representation of this times a finite rank operator, some operator of the form. So, for example, operator of rank 1. So an operator of rank 1 would be some maybe some vector. Some vector. What's a good name for a vector? Like maybe I have a, I don't know, like A, an element in 0, and I have L, an element in M0 dual. So then I have rank 1 operator, namely V goes to L of V times A. So maybe call this operator something. Just call it that. So times here I have this my rank 1 operator, and then this other factor I take. This would be so this would be if I take a trace over auxiliary space. If I take a matrix element in auxiliary space, then I get an element in endomorphisms of my M. So this is sorry. This is not quite done yet. We'd like to endomorphisms tensor. So this we would like. Right. So this would be so. A was a very unfortunate choice. Since A is some variable here. So maybe we call this variable U now. So this is now this is a rational function, which we can also we can expand in, say, in around infinity, since at u equals infinity, this identity, it's not a very interesting operator. Maybe we expand it around infinity, and we pick a coefficient. So we pick a coefficient by coefficients of the matrices, coefficients in the infinity expansion. And so what do we need to check? That this is it's really warm in this room. So this is tautologically a bialgebra. The reason it's bialgebra is it already acts in all possible tensor products. Right? So concretely, what does it mean? Concretely, if I want so like if I want to say that this is so in other words, this is what does it mean? If I take a tensor product of this guy with itself, there's a natural map from this product to the tensor product by itself, just because the set is already included in the other set. But what does it mean concretely? That if I take my R matrix. R matrix, it's an operator in this in the has somehow two entries, right? So there's a, let me call it, there's the zeroth entry and the first entry. And if I take it 1 tensor the coproduct, this is how it's now supposed to act in the tensor product of two things. And so that would be how it acts. By the scheme, it now will have to act in, so by the scheme, if I now act in the tensor product of two things, so if I have a, here's my, was my M0, and now tensor product of two things. And so this means I first have to braid M0 with M1 and then M0 with M2. So this means that if I take this coproduct, this is 0, 1, 2. If I take the matrix coefficient in the zeroth factor and the coproduct in the second factor, that means I have to take the zeroth coefficient in this expression. That's what it's concrete. All right. Now, what are the why is the R matrix itself is the intertwiner? So I would like to say that, then if I'd like to say, so this means we have to compare R12, which is after all, so R12 is this expression. So it's R01 with R02. And now by Young-Baxter equation, this is the same as if I take R01, R02 in, or I have the Young-Baxter equation here. So if I take them in the opposite order, then this is the same as if I take this one R12 here and R12 inverse there. So that this says that maybe I'll have it in different colors. So this is by Young-Baxter. R12 inverse R12. So this says, we're just going to copy this. So it will be R12 inverse R021. R12. This really says that the tensor product in one order is isomorphic to the tensor product with the other order if you apply this R. Okay? So R is the braiding. That makes sense. It means that this means that my module, if I so this means that so my module M1 tensor 2, my algebra acts on this module by the matrix coefficients of this. And now if I apply, if I'd like instead act on this in the opposite way, then I have to apply the R matrix. So R matrix is really the braiding for this category. next way is any element in the so any element in the commutant Y gives a relation. Commutant in this big space. Because suppose if I have suppose I have some operator. Suppose I have a non-zero intertwiner between some relation. So suppose I have some map. We call it, I don't know, like M1. Just for the sake of the argument, with some map going to some M3, some map phi, which is an intertwiner. This means I can take this. What does it mean? That if I take this guy and I tensor it with anything else, then this map commutes with all R matrices. I mean, what does it mean to commute with all elements of the Yang? It means if I take the R matrix between this module and that's some other module, and this module is some other module, then I get the quality of R matrices. But now I can read this also backwards. This relation I can read backwards, and says that this means some particular matrix coefficients of R matrix are equal to some other matrix coefficients of R matrix. Okay, so this means a relation. In this case, would be something quadratic equals, some kind of quadratic relation in my Yangian equals something linear. Could be, I don't know, 5 factors on one side. But some maybe could be direct sum of many tensor factors. Could be some polynomial relation in my Yangian. For example, we have the R matrix. So in particular, there's an R matrix itself. So there's for any M1, M2. We can put them in a different order using the R matrix. It's an example of this. And then this says the R matrix itself is an example of a commutation relation. It tells you if I take, so it means I have a quadratic relation in my Yangian. Because what's a matrix elements in here, since it's a matrix element in my tensor product, a matrix element in a tensor product is a product of matrix elements. So a matrix element in here is some quadratic expression in R matrices, in my original R matrices, and then it's equal to some other quadratic expression in original R matrices. It's a relation. And so what's this relation deformed? So if I have a like a semi-simple algebraic group acting in some, so if I have concretely we can ask for, like, I don't know, like GLN or GL2. Let's see. So GL2, this acts in direct sum from k goes from 0 to infinity, and that's C2 tensor power k. this is going to be a not very interesting statement here, which says the matrix elements of this representation are all possible. In fact, somehow, all possible polynomial expression in the matrix coefficients of so there's means if I have a the action of JL2 just acts on C2, the matrix coefficients of this are the coordinates in my group, defining representation. And so these are all polynomial, the matrix coefficients here are all polynomial expression in my group. And the only thing that they satisfy, and since it's an open set of a vector space, the only thing that they satisfy is that they all, they're commutative polynomials. Right? So if I write some, so this is this acts by matrices in x1, 1, x1, 2, x2, 1, x2, 2. This comes from the x2. And so the fact that the representation in different orders are the same just means the polynomials, x1, 2, x2, 1 equals just commute. But if I had some subgroup in here, then there will be more. Like for example, if instead of the full linear group, I took like orthogonal. Let's for the sake of argument call it R. If I have some subgroup, then of course I have more intertwinings. Like for example, orthogonal group, there would be a quadratic. There's an intertwiner between CR tensor square and the trivial representation, and that intertwiner corresponds to the next relation that I have in orthogonal group. In general, there's a relation due to going back to Hermann Weyl by saying that if I want to describe the if an algebraic group and I want to describe its image in a representation, this is the same as being able to decompose all tensor powers of the representation. And this is a deformed version of that. In particular, the invariance with respect to symmetric group, it becomes it's broken. There's an R matrix instead of symmetric group. They not exactly commute the degenerators of the Yang. They commute. There's an R matrix which enters this commutation relation. And similarly, if I were thinking about the orthogonal group, that there'll be the square of the defining representation will be non-trivial intertwined with that in the trivial representation. That will be a relation. So this is why I've. So this is a little detour, maybe. But so as the name suggests, Yang-Baxter relation. This is some relation that arose in quantum integral system long before the invention of quantum groups by Drinfeld and Gibbon. So so this is the reason. So the Yang-Baxter equation was a way to so maybe the Baxter idea. Baxter idea is that the Yang-Baxter equation gives rise to interesting commuting operator. And this is how this quantum integrable spin chain this is the story which I'm going to try to tell now. And this discussion here is that maybe, sorry if I've maybe, could I be forgiven for oversimplifying history dramatically? But this is especially since it's being videotaped, so this maybe not a good idea. But somehow when the quantum groups were invented by Jimbo and Drinfeld, so this was, I mean, still is a very important source. So there's like there's a source, the quantum groups. It's a very important source of solutions to Young-Baxter equation. So and therefore a very interesting, and therefore gives you a very interesting supply of quantum integrable systems. What I've been explaining here is that maybe in fact there's some kind of loop here. So there's somehow you can this is like a relation with chicken and the egg. So you can start with if you have an egg, you can get a chicken. If you have a chicken, you can get an egg. And so then there's in fact in the where I'm going is that there is also we will maybe too late today, but we'll see. So there is a slightly different way to, like, maybe another vertex in this triangle. There is a so there's quantum groups by the work of, especially by works of Nakajima. So there's like a geometric action of quantum groups. So geometric actions of quantum groups. Which is maybe some loosely defined, some geometry, and you can go there's some kind of triangle here where you can go in all possible directions. So instead of starting with the quantum group and getting solution Young-Baxter and also getting a geometric action of the quantum group, you can maybe geometrically first construct the solution of Young-Baxter equation. So if you geometrically construct the solution of Young-Baxter equation, then you get, by the yoga I explained, you can also get automatically a solution of an action of a quantum group. So there's some geometric construction which I was planning to explain today. Well, we'll see how far I can go. I'll get. So there's some, like I said, so you can if you have a quantum group, you can get solution Young-Baxter. If you have a solution Young-Baxter, you can get a quantum group. And now, if you're interested in some geometric incarnation of this picture, you can also you can have a different perspective of what we're going to get first. So first you can first geometrically define an action of a quantum group, and then of course you're going to get a solution Young-Baxter. Or you can geometrically define solution Young-Baxter, then you're going to get a geometrically defined action of a quantum group. So there's a, in other words, you can, these things are really, right, so I think there's only so many paths you can take in a graph with 3 vertices and 3 edges, and so I think I took them already many times. So first I'll explain this. And this was actually in the context of, first in the context of vertex model, for which the spin chain is not, I mean, it's equivalent, but not. So vertex models of the statistical mechanics. This Baxter's main interest. So what's a vertex model? You have a graph, which is maybe we'll start with some graph which looks like a regular graph, something like this. And so, right, the lines in this graph are oriented. This is important. And then maybe some part of this graph which is which is not really regular. So maybe I'll do something like it. Right now, on the edges of this graph, leave some degrees of freedom that takes values in some representation. So maybe there's some representation. Maybe I call it, I don't know, to every line corresponds representation. You can call it M1, M2, M3, M4, M4. And at every edge, so representation corresponds to a line, but the variables live on an edge. So for every, like, you know, from here to here, lives some variable, we call it sigma, sigma of this edge. And then there's some other sigma which sits on the silver. And then this takes a value in this representation. And they interact via, so if I have, they count the vertex, so there's M1, M2, and then there is sigma 1, sigma 2, sigma 2 prime, sigma 1 prime. And there is an interaction weight which is an operator. You can view this as a matrix element of an operator in a tensor product of these two. So sigma 1, sigma 2, sigma 1 prime, sigma 2 prime. This is really the element in the morphisms of M1, tensor M2. And one is, the main interest is to compute the partition function of such model with some given boundary conditions. So boundary conditions means I fix the variables at all unbounded edges. So maybe so this sigma, this one fluctuates, but there's some, I don't know, there's some sigma, whatever, some. So to every unbounded edge, maybe there's an edge, this is edge E, and there's sigma of E, and then there's unbounded edge, which I'll denote E boundary, and then there's a sigma of E boundary. And so this means that what the partition function means, it's a map from incoming boundaries, as incoming boundary and outgoing boundary according to the orientation of my lines. And there's a map from the tensor packer of incoming guys to the outgoing ones, which depend by contraction indices in this diagram. Like typically, the most typical one is everybody's favorite is the partition function on the torus with periodic boundary conditions, where you draw this. And then you close all this looks like this. Then you get a number, which is interpreted as a partition function. I mean, the geometry here is the graph sits on the torus, and then you get the you sum over all possible values, so all edges are bounded, so you get you sum over all possible indices in the on these edges, and there's some interaction strength, which is given by this matrix, and so then you get. So this would be this is everybody's favorite example. And so this of course you can compute this. So if maybe there's a maybe let me add one more here, so that to avoid further confusion. This is slightly unconventional, maybe. This is slightly unconventional contraction of indices, but to make it a more conventional contraction of indices, we can consider this such operator here. So this would be going from maybe M1, M2, M3, so forth, and then there's some variable M0, and then we can contract this indices. So sorry, there's no equality yet. So that if there is some, so this is maybe called, let's say M0 here, M0 prime here, M0 double prime there, and so forth, and then M1, M2, M3, so forth. This is an operator. This is an endomorphisms of the tensor product from I going from 1 to n, T I. Maybe we'll call this matrix T M0. Then this contracted partition function on the torus is Tm0, Tm0 prime, so forth straight. Oh, interesting audio effect. That clear? So in particular, so let's say that this is so in particular it'd be great if these guys can be simultaneously diagonalized. That'd be just great, because then we could compute the partition function on the torus by just well, if they're all diagonal matrices, they're diagonal in some basis. Well, we'll just multiply them all, okay? And that'd be the answer. So this is called transfer matrix. In general, transfer matrix is a general notion in statistical mechanics, or it's also in combinatorics. If you have some combinatorial problem of the structure which has a product structure, and you break it in layers, and then you can make some intermediate summation, and then to express the overall summation as a product of matrices. It's called a transfer matrix. So if by chance it turns out that this commute can be simultaneously diagonalized, then like I said, this is great, because I mean, for most for many so maybe it's too late in the lecture to go into discussion of general features of statistical mechanics. Maybe in the list of references I gave a book by Jim Ben-Mee, which is great. I mean, it's hard reading from the mid along, but the beginning is great reading, and so you can enjoy this. And so this is in two-dimensional statistical, general statistical mechanics, it's usually very hard to get past the simplest, to get theoretically past the very simplest properties of your models. Like, for example, if you know just, say, if you have a partition function on the torus, and you just know how it's like the logarithm multiplication function scales as the torus gets larger and larger, this is already extremely valuable. And so this is, if you have a way to diagonalize these matrices, then you'd know, for example, what would be the scaling of this partition function as say this product gets longer and longer. And it's harder to know what will be if this product gets longer and longer. But so Baxter's idea says that the Young-Baxter equation is precisely a tool to produce commuting transfer matrices. So it's precisely so. Baxter's observation is that if you have if the vertex interaction, so the R matrix here is just a collection of numbers, which numbers parameterized by some basis in some vector space. And so there's it's no good reason to require anything special of that collection. But if it satisfies Young-Baxter equation, then what the Young-Baxter equation says? Young-Baxter equation says that if I have three lines like this, so this is an operator from this is an operator from product of three spaces. If this product equals the other in the other way around, you can have it like this or like that. In other words, if you can change your lattice by a move like this without affecting the partition function with given boundary. Here the boundary, there's six unbounded edges, so it means you have a three-valent tensor, three lower three upper indices. If this is satisfied, this is Young-Baxter equation. And Baxter observation is precisely a Young-Baxter equation, then the transfer matrix is commute. So Baxter says that if the Young-Baxter equation implies and Young-Baxter and plus invertibility of R plus R is invertible, this implies that the transfer matrix is really commute. This is a remarkable argument. What does it? So how does it go? It says, then if I take, it says consider this diagram. And then here we put the maybe I put the inverse here of the matrix. Here I put. to say? So just here put like the inverse. This is my M 0 prime 0 prime. So this is something we can consider. So if I assume it has an inverse, so then by the Young-Baxter move, we can take this triangle, and we can flip it. So it means this would be equal to, I start with this, and then I cross, and then I continue. So means I can bring this crossing all the way to here where it cancels. And so then this means that this is equal to M0, 1. I should have put it in the so this is just a product. This is T M0 T M 0 prime. This is on one hand. On the other hand, so not the product. This is just the before I take the trace. So this is a product of things of which I will take the trace. T is when the transfer matrix is when I take this. I take this expression and take its trace. Now I haven't taken the trace yet, but I can now take the trace, and I'm going to get the. If I take the trace, then trace over M0 tensor M0 prime, then I'm going to get T M0 T M0 prime. On the other hand, I could take trace here. So if I take this same trace, then so here I have in my auxiliary space. So this matrix R acts in this auxiliary space over which I take the trace. So I take the trace. Let me go back to it again. Takes M0 tensor M0 prime, and this is where that. So this crossing here, and its inverse crossing there. This is where this R matrices act. R M0 R M0 prime. I have some operator. And here I multiply by this matrix, and there I multiply by its inverse of that matrix. But of course, that's not going to change the trace. So under the trace side, this will be the same as the trace of, or you can say you can say it differently. You can say, what does it mean to take the trace? To take the trace, we can take this guy and loop it like that, right? This is what it means to take the trace. But if we loop it like this, that we can bring this, then on the cylinder, these two guys are just really together. And on the cylinder, this guy, so this guy just really cancel. Maybe let's do it like this. Let's just loop this thing. And so here I get these guys are looped like this. And this is the T M0, T M0 prime. And on the other hand, if I just cancel it through the infinity, then I'm going to get whereas now M0 sits here, and M0 prime sits there. So I'm going to get T M0 prime, T M0. I might have said many incoherent things in this talk, but this one thing is really, really simple, really beautiful. And so maybe if you may be confused about other things, but maybe I hope you understand this. If you don't, maybe we can pause and somehow discuss it more, because this is really basic. If it's something non-clear, maybe I can try to clarify. And generalization is suppose is this twisted boundary condition or quasi-periodic boundary condition. This means suppose let G be an operator in all Mi. So we think of it like a group element that acts in all of these tensor products, such that J tensor G commutes with all our matrices. Then and what you can do is you can define a twist everywhere by identifying what happens here. Here, when we take the periodic boundary condition, it really means we take the degrees of freedom here on this outgoing edge and really identify them with the ones on incoming edge. Instead, we could use, if you remember the discussion of this quasi-periodic boundary condition in the spin chain, what you can do is you can act by some element G as you identify it. In other words, you define this transfer matrix, you define as the trace of over M0 of G tensor 1. It's an element that acts in the first tensor factor in this factor only of times the R matrix of M0 and then the degrees of 10. This is just like before, except when you take the trace, you can put a twist. And so what will happen in this picture? In this picture, we want to take, this means here, I can put G and G here. You see, G tensor G commutes with R matrices. So I can bring this dot past this G and G. And the rest is the same. So I get G, 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 G. then this matrix is then Tm0. So what do you commute what for any for a fixed G? So this depends. In other words, this is a function of a representation and an element. And this means that the commutator of T M0, maybe G, the commutator of T M0 prime G, this commutator is 0. Means these can be different, but these are the same. Okay, that was a long discussion. We haven't seen a single R matrix yet. And so, for like the glory of the subject is more complicated R matrices, which you can, I hope you can somehow motivate it enough to open some literature on them. But there's the simplest one of them, which you always remember. Is that so? This will be an R matrix, this Yang R matrix. It says so. This operates in the tensor product of CR tensor CR, and what it is the R of U is 1 minus 1 over U times the permutation. In fact, for dimensional reasons, so for us, U will be some variable. It's best to introduce a new variable, which is completely silly right now. But for geometric reasons, it's important because this will be some meaningful. This will be some element, and this will be some element. It's like has some cohomological degrees. This too. Yeah. And this solves Yang-Baxter equation. You can. Not difficult to check directly. And so this commutes. This commutes with whole GLR. Right? That's clear? And so we get like this many choices for this. XG. And so the conclusion is that if I take this, this R matrix, we get the Yangian of GLR as a subalgebra in the product. Of you can right and if you take CR some variable A1. We discussed this already for in the antiform, this deforms the universal developing of I mean, why is it has the same number of? I mean, why does it? So this deforms universal developing of GL R tensor polynomials in one variable. So as and so what? So why is that? It's. I mean, first, how many operators are we going to get? So we get there's really only one auxiliary representation you can get, so which is I mean, this just CR. Everything else will be so the matrix. So you take tensor products of auxiliary representation. You get just products of elements in the Yang. So the number of generators would be just you take one auxiliary representation. So you get R square matrix elements there, and then you get expansion to infinity, which means you get countably many copies of R by R matrices as your generator. Well, this is already what you have here. And then if you take your R matrix and you take, of course, this R matrix, it's non-trivial matrix element, all vanish modulo H bar. And if H bar is 0, then it's, this matrix is 1. But if you take it modulo H bar square, and you look at the coefficient of H bar, it's like just like we did with this reduced virtual class type of computation. Then in this form, it's easy to see that you get, in fact, you really get this universal developing algebra. I mean, exactly how it acts in this representation. So you get an algebra which is certainly going to be of the exact same size as this algebra. It's a whole algebra where we can. And it's only going to have, since it's only going to have one relation, namely corresponding to the one kind of relation, corresponding to the one interesting, and all intertwiners here are just R matrices, corresponding to the fact that in the commuted situation it's just a permutation. And so you're going to get just one kind of relation, and that would be that's this deformation. And then so this has Baxter subalgebras parameterized by G, and the really different ones modulo conjugate G in GLN modulo conjugation in center. So this really one of the interesting ones are of the form the red Z2 ZR. I know that not every element in GLN is conjugate to diagonal matrix, but this the algebra they form. This is the interesting really ones. And remember, we were interested in the case where R is equal to 2. So in this case, we'll have this one. And so this one here, for R equals 2, one can check. Without the energy. with that energy. That's summation I plus 1 from 1 goes to 1 to n with this quasi-periodic boundary condition. This quasi-periodic boundary condition belongs to the Baxter subalgebra. It's not an entirely trivial computation, but can be something done. And so this says that this mechanism, this Baxter mechanism, of producing many commuting operators. It works not only for this lattice model, but also for related models of quantum. This is quantum mechanics, namely in this case as a spin chain. This says that this is this gives a big supply of. This gives a maximal commutative subalgebra, in fact, of operators that contain my Hamiltonian. And so this is how this is maybe halfway to solving, because this is well, I don't know. I mean, it depends. Maybe roughly halfway. So you have some operator, and you want to know its spectrum and the eigenvalues. Sorry, eigenvalues and the eigenvectors. And then if you found the big non-commutative algebra, some interesting non-commutative algebra with a big commutative subalgebra, such that your operator belongs to the image of this commutative subalgebra, then it's certainly a big success. And you can count on being, well, not count. You can somehow reasonably hope that studying further properties of this algebra, you'd be able to. Oh no, I'm almost at the end of my lecture. So okay, yeah, right. So then somehow, okay. I was saying general things anyway. So studying properties of this algebra, you may be able to actually diagonalize it. But the actual route which we're going to take is different. So plan for, there's only one lecture remaining, and it's going to be a little tight because so maybe the plan for the remaining lecture to explain them consists of two things which we'll try to accomplish, and the first is to construct C, or maybe C, this R matrix geometrically. Because if you can see the R matrix by, then you can, like I said, you see the action, see the R matrix, see the action of the Yankee. And the second thing is that maybe so geometrically. So I apologize. I've been going over time every single lecture since maybe, with the exception of lecture 1. I was really hoping not to do it today. But maybe I'll take 1 minute to explain since it's important somehow. Find maybe I'll write find eigenvalues and I'm permitting eigenvectors geometrical. You see the geometric, I mean, I guess you live here in Kyoto, then you know that geometric representation theory is very powerful. But it's powerful and somehow concretely powerful. It means you can really solve problems geometrically, which is hard to solve in general. And the reason it's hard is that suppose there's so remember we had this operator, which was this operator of quantum multiplication. So plus, well, maybe minus here. It doesn't really matter. So just take the pair. There's no sum. It's just Grassmannian. So you pair this with the generator, the curve T1, and this is Z minus Z. Yeah. That sort of expression. Some matrix depends on Z. And you need to, and the problem here, since this belongs to the same algebra as this guy, is to be able to diagonalize this operator. But geometrically, you can solve more general equations. So geometrically, you can solve equation of the following form: that if you have some function, so it's an equation for unknown function of psi. So if I take sub psi of z, and I will give myself some new variable, call it epsilon, it will satisfy a equation of the form z d by dz is equal to psi z. This is what's called quantum differential equation. Geometrically, there's a way to solve this. I mean, geometrically, there's a solution to this equation. If you understand enough, somehow it's a question of what you understand about the solution, but at least there's some solution. And this is strictly more general than solving defining the eigenvectors and eigenvalues. Suppose you have some equation of this form, and what's going to happen if this epsilon goes to 0? That if epsilon goes to 0 in an equation like this, then we have a equation, and the coefficient in front of the derivative goes to 0. Then the solution is going to look like this. It's going to be like exponential 1 over epsilon, like the integral of the eigenvalue times the eigenvector. So if you understand enough about solving differential equation, you of course certainly understand enough about the eigenvalue problem. It gives you this eigenvector and eigenvalue. And what Nekrasov-Tashvili really computed, they computed this. This is easier to compute. This is an overall factor. I mean, if you imagine this is some matrix, and this is some factor. And it's like enough to know one row of this matrix to compute this. And time permitting, we can talk about this. And so then they computed this, and then they see the spectrum. All right, so this was 5 minutes over time. This is all for today. Thank you.